So yesterday we argued that for the hydrogen atom problem or hydrogen-like atoms, your radials equation should have, or we looked at an ansatz where your radial equation has a form given by equation 2. Okay. So basically we plug this form back in the differential equation for u, and then we derived a differential equation for capital F of rho. Capital F of rho is again a function that we do not yet know. Okay. So let me write this first ansatz here. So u of rho, we argued, should look something like rho to the L plus 1 e to the minus rho times F of rho. And this form is motivated by the observation that we know that for small enough values of the distance, you should have some kind of a power series of order L. And for large enough distances, since we are looking at bound states, these guys should die down at infinity. So we are looking at e to the minus rho. And then we are looking at some function F of rho that sort of interpolates between these two extrema. So to find F of rho, we set up the differential equation for capital F and we tried a power series. And the power series gave us a relation between the successive coefficients. And this is called the recursion relation between the coefficients. And this is the place where we stopped last time. So let me write this recursion relation again. AS plus 1 equals minus C plus 2L plus 2S plus 2 times AS. Okay. And then let's remind ourselves that this C is equal to 2 mu Z E square divided by kappa H bar square. Okay. And remember that E is minus H bar square kappa square over 2. All right. So we can go ahead now at this point, if you're just doing rote differential equations in mathematical physics, we can simply go ahead at this point and solve this differential equation and get the actual solutions. But we'll follow a slightly different strategy. We are interested in understanding the asymptotic limit of this power series. In other words, we are trying to look at what happens when rho becomes very, very large. Now we know that when rho becomes very, very large, we want to have a radial equation to die at infinity because we don't want it to grow like, any power series or any exponential series, because otherwise my wave function will not be normalizable. So I have to ensure that F of rho satisfies this condition. So to understand what happens at very, very large distances, let me look at terms in the power series for very large S. Okay, because remember that my F of rho is S equals 0 to infinity, AS rho to the S. So if I'm looking at very, very large distances, I'm looking at very large rho. So it's the larger powers that contribute, not the smaller powers. So rho to the 10 is more important than rho to the 2 and so on and so forth for large distances. So let me look at very large distances in which I'm interested in the terms that are made up of large S's. So for very large S, for S goes to infinity, let us understand the structure of this recursion relation. What is the structure of this recursion relation? Well, since S is very, very large compared to things like, for any value of L, I'm looking at S very, very large. So I'll neglect things like 2 and 2L and things like that in this equation and write this equation as S. So S plus 2L plus 2 simply becomes S. And S plus 1 is also S because for very large S, 1 is negligible compared to S. So the first term goes like S squared times AS plus 1. And this is equal to, I'll assume that we are looking at C. C is composed of some physical parameters. I'll assume that all this is very small because we are looking at very, very large S's. So I will neglect everything except the 2S part in the right-hand side of this equation. And this little 2 is actually very important, as you will discover in just a second. So in the asymptotic limit as S goes to infinity or very, very large distances, the relation between the coefficients AS plus 1 over AS has the form 2 divided by S. Okay. And there is actually, no, instead of solving this, we can actually guess what power series this would be. In fact, we exactly know what is the power series in which the successive coefficients go like 1 over s. The ratio of successive coefficients goes like 1 over s. Okay, and this is the exponential series. So this is a telltale property of the exponential series. Exponential series. Okay. Why is that? Well, let us actually investigate. So let us look at something like e to the 2 rho. What is e to the 2 rho? This is equal to s is equal to 0 to infinity 2 rho to the s over s factorial, right? This is the definition of the exponential series. E to the x is x to the s over s factorial summed over all s. So I can write this as s is equal to 0 to infinity 2 to the s over s factorial times rho to the s. Okay. So what are the coefficients? The coefficients of the sth term of this series is 2 to the s over s factorial. And the coefficient of the s plus 1th term is obviously 2 to the s plus 1 divided by s plus 1 factorial. And as you very well know, this is 2 to the s plus 1 divided by s plus 1 times s factorial, right? So for very, very large s's, for an exponential series, the ratio of the successive coefficients goes to 2 to the s plus 1 divided by s factorial. And since I'm looking at very, very large s's, I will approximate s plus 1 as just s times s factorial divided by 2 to the s, which is 2 over s. Okay. So this property that our capital F function has is a telltale sign that what we are actually looking at in the asymptotic limit is actually the exponential series, and not just any exponential series, it is e to the 2 rho. Okay. Now, much of what we will say would be moot if it was just e to the rho. So the 2 is actually very important. So what do we find? So we know that f of rho should go like e to the 2 rho. Now it can be multiplied by some other function of rho for other values of distances. I do not know, but for very large distances, it does go like e to the 2 rho, which means my u of rho, which is equal to rho to the L plus 1 e to the minus rho f of rho for large distances goes like rho to the L plus 1 e to the minus rho times e to the 2 rho, which goes like e to the rho. And this is a problem. This is a problem because this means that u of rho is not a normalizable function. Okay, and this is a huge mess because we are looking for bound states, and bound states are normalizable functions which have the nice property that as you go far enough away, your wave functions should all die down very nicely. So we have a contradiction. The contradiction is that we are looking for bound states, but the differential equation that we set up for f of rho, when we wrote down as a general power series as with s going from 0 to infinity, admits an exponential solution for very large distances. And if you plug this back, if it was e to the rho, then it would still be okay because e to the rho times e to the minus rho is just 1. So at least, we can hope that whatever is multiplying this f of rho will sort of cancel this rho to the L plus 1. But we have no hope here because if it goes like e to the 2 rho, the radial wave function exponentially blows up for large distances. So what is the solution? What is the way out? The only way out is to recognize that there is something wrong with our consorts here. We looked at a power series solution, and power series solution is usually a very logical thing to look for. But the only way we can ensure that we can still have a power series solution and not have things blow up as rho goes to very, very large values is by not adding up terms which for all values of S, but to terminate this power series at some value of S. Okay, so we can still have a power series solution. There is nothing wrong with that. But if we want a solution that doesn't blow up, we better not have all terms in the power series. So we will demand that we are still looking for a power series. So solution, look for a power series but one that terminates at some value of S. I don't know what value of S. It can be as low or as high as it wants, but it has to terminate at some value of S. As long as I don't add up infinite terms, I will not recover the exponential series, because exponential is strictly a sum of infinite powers, right? So if I stop at any finite powers, I will not recover an exponential series. So I will hope that this truncated power series would give me a bound state solution for the hydrogen atom problem. But how will I truncate the power series? So again, look at the recursion relation. S plus 2L plus 2 times S plus 1, AS plus 1 equals minus C plus 2S plus 2L plus 2 times AS. So when I say that the series has to truncate, I mean that after a certain S, whatever that S is, it can be 1, 0, 3, 5, 100, whatever it is, after some value of S, the next coefficient should be identically 0. Once the next coefficient is 0, it guarantees that all the other coefficients, successive coefficients, are also 0, because AS plus 1 is related to AS. So if A99 is non-zero, but A100 is 0, then if you plug A100 into this equation, it will immediately tell you that A101 is also 0, because A101 is related to A100, and so on and so forth. So if you make sure that for the coefficient at some value of S is equal to 0, then you can guarantee that the power series will terminate. Now, the left-hand side is basically a non-vanishing function of S and L, but the right-hand side can be vanishing. It can vanish. So AS plus 1 can vanish if minus C plus 2S plus 2L plus 2 equals 0. Okay. In other words, AS plus 1 would be equal to 0. In other words, your C. Remember that C is a function of the physical parameters of the problem. And this function of the physical parameters of the problem should be equal to 2 times S plus L plus 1. S is an integer, L is an integer, 1 is obviously an integer. So S plus L plus 1 is also an integer, which I will call as N. So this function of physical parameters C should be actually 2 times some integer. If this is true, then my power series is guaranteed to stop at some particular point. And this is all I need to show that the energies are quantized for this bound state problem, because C, as we just wrote down here, is related to kappa, and kappa is related to the energy. Okay. So again, the point here is, I did not solve the differential equation by force. If I had solved it, I would have gotten the exact formulation for capital F of rho. But what I did was basically argue on physical grounds that for large rho, F of rho cannot blow up. So this forced me to look for a power series solution that is not a sum of infinite terms, but stops at some particular value. The only way I can guarantee that the coefficients vanish after a certain point is if this C is equal to some twice of some integer, and this integer I'm calling N. Now there's a whole bunch of integers floating around, so don't be confused. This N is equal to S plus L plus 1. And S can be anything at this point, right? Okay. But what is L? Remember our motivation for L, we demand that the radial function u of rho goes like rho to the L plus 1 for very, very small distances. So L determines the behavior of the radial wave function for very, very small distances rho. Okay. All right. So what does this whole thing give us? So let us plug this back into the equation for C and then find out. So C is equal to 2n. Now this is, so let me write down C again because I missed it over here. 2 mu z square over kappa h. 2 mu z e square over kappa h bar square is 2n. Okay. And I can, oh, this is not showing. So let me, sorry. Sorry, give me 1 second. Okay. So this is my C. Okay. And this tells me that mu z e square over kappa h bar square is an integer. So remember that the right hand side is a dimensionless quantity. It is an integer. So there is a question, can we take f to be e to the minus 2 rho? We would only get a power of minus 1 then. So where is it? No, the power series for e to the minus 2 rho is very different from the power series for e to the rho. So if you look at e to the minus 2 rho, then this would be the successive coefficient. So this would be s is equal to 0 to infinity minus 2 over s to the s plus 1. Sorry, s rho to the s, right? So as plus 1 divided by as for this would be minus 2 to the s plus 1 divided by s plus 1 factorial times s factorial divided by minus 2 to the s, right? So then there will be a factor of minus 1 as you correctly point out, and this is markedly different from e to the 2 rho definition where the terms do not alternate at all. So this would be minus 2 divided by s. Okay. This power series, this ratio of coefficients is different from the power series coefficient for e to the 2 rho. What we have, we manifestly found out that as plus 1 over as is actually plus 2 over s, not minus 2 over s. Okay. So the plus minus difference is not just semantics, it is very important. It tells you that they are two completely different power series. And if it is minus 2s, yes, you're absolutely right. Things would work out, but it is not. So we cannot impose it to be.
Hello, sir.
Yes.
So here is one thing I don't understand.
Huh?
When I am considering a stands to infinity, I mean larger distance, then the higher term of the power series should contribute more. But here I am terminating our power series into a finite polynomial. So how I am getting the right answer?
How you are getting the, what's the last part?
Right answer?
Right answer. Okay. See, this is an argument based on physical grounds. So suppose if you simply look at this power series solution, you're absolutely right. For very, very large distances, larger terms should contribute, right? So if you keep all terms to infinity, then you actually find that the power series actually blows up. We don't want the power series to blow up because we are looking for normalizable wave functions. So the only way out within this constraint, we can solve the differential equation in any other way we want, but we will always get the same answer. The only way out is to demand that, see, the whole problem arises because I keep adding infinite number of terms and the addition is such that it gives me e to the rho, e to the 2 rho, right? But if I artificially cut off this series at some value of s, whatever value of s it is, we will come to that question a little later. If I simply cut it off, I would not get an exponential growth because the exponential series is the sum of all infinite number of terms. Okay. So remember that it can be still very large. I don't care. So it can go like, as long as it terminates in some value of S, even if it is large, the wave function is guaranteed to be normalizing. That is all I care about. I just don't want it to become absolutely infinity, because e to the rho goes to infinity as rho goes to infinity. Okay.
So can we do that? That for our own purpose, we can terminate an infinite power series into a finite polynomial.
Absolutely, because we are doing physics, not mathematics.
Okay, sir.
We are looking for bound state solutions. Okay. Any other questions?
No, sir.
Anybody else? Okay. So hopefully this should show up correctly this time. Okay. So suppose if I square this equation, what do I get? So kappa square is mu square z square e to the fourth divided by n square h bar to the fourth, and I will substitute kappa square equals minus 2 mu e over h bar square. So I'll substitute this is equal to minus 2 mu e over h bar square equals mu square z square e to the fourth over n square h bar to the fourth, which tells me that your energies actually are quantized by some 1 over n square times some fundamental number, and this fundamental number is mu z square e to the fourth divided by 2 h bar square, right? I got that right. Times 1 over n square. Okay, this is the famous quantized energies of the hydrogen atom, and you see that the energies go like 1 over n square. So as remember, n is equal to s plus l plus 1. So if I look at larger and larger values of n, the energies of such states become smaller and smaller. Okay, it goes like 1 over n square. That is the first point. Okay. Now the other thing is there is also a fundamental length scale that has emerged in this problem. So if you look at this equation, okay, if you look at that equation, you can turn this around and say that since the right hand side is a number, a dimensionless quantity, I can write the left hand side as 1 over kappa times h bar square over mu z e square equals n. Okay. Now kappa, as you know, is a wave number which has the units of 1 over length. So if the left hand side is also to be dimensionless, then whatever is multiplying kappa should have the units of length. Because kappa has the dimensions of 1 over length, if it is multiplied by something that has the dimensions of length, the entire thing would be dimensionless. So this defines a fundamental length scale in the problem, and we call this A, which is h bar square over mu z e square. And this is called the Bohr radius. Okay, and numerically, I think this has some value. If I remember right, something like 0.53 angstroms, 10 to the minus 10 meter, z to the minus 1. Okay, for atoms with larger atomic numbers, this number is smaller and smaller. Okay, so this kappa n you can write basically as 1 over na, okay, which means that the electron is confined to some distance of order na. So what have we found thus far? We have found that, so we still have to figure out what the capital F are, but we can solve that equation, solve the differential equation, which I will do in a handout later. And this F of rho's, remember now they are actually not a power series of infinite number of terms, but they only have a finite number of terms. And these are what are called the Laguerre polynomials. Okay. And apart from some normalizations, F equals, so before I do that, let me actually tell you that we defined this n as s plus l plus 1. So I can turn this around and write l as n minus s minus 1. Okay. Now, what is the lowest value of s? Well, equal to 0. And what is the largest value of s? Well, whatever it is. But what is the lowest value of L? We already argued that L is an integer, so the lowest value of L is 0. So what is the largest value of L? Well, this equation tells us. Up till now, we've never figured out the largest value of L, but we know that for a given n, the largest value of L occurs for s is equal to 0. So L is a number that can go from 0 to n minus 1. Okay. Remember that if s keeps increasing, L keeps decreasing. So the largest value of L occurs for s is equal to 0 for a given value of n. Okay, so L is a number that can go from 0 to n minus 1, and n is called the principal quantum number. So then, what is the degeneracy in the problem? So this is something that you should pay attention to, and I'll talk about this, and then we will write down f for a couple of values of n. There is a lot of degeneracy in this problem. Okay, why? So let us say that you fix some n. Okay, for this, no, remember that why are we fixing n? Because the energy of the bound states goes only like n. They don't know about L or the azimuthal quantum number m. They only go like n. So suppose if we fix n, and En goes like 1 over n square. For a given n, L can go from 0 to n minus 1. So for fixed n, L goes from 0 to n minus 1. But we already argued that for a given L, m takes minus L to plus L, which is equal to 2L plus 1 values. Okay. So suppose if you fix n, then how many states are there that have the exact same energy? Instead of doing the sum, let us actually work this out for, let us say some very trivial number. So let us say n equals 2. For n equal to 2, L can be 0 or 1. Right? If L equal to 0, m can be only 0. And if L equal to 1, m can be minus 1, 0, and 1. Right? So how many different states are possible? There is a state with n equal to 2, L equal to 0, m equal to 0. That is one possibility. N equal to 2, L equal to 1, m equal to minus 1. N equals 2, L equals 1, m equals 0. And n equals 2, L equals 1, m equals minus 1. Which means all these 4 states that each have different values of L and m all have the exact same energy En. This is an important property, and this is a reflection of the rotational symmetry of the problem. Well, not completely, but at least the degeneracy in m is due to the rotational invariance in the problem. Okay, so what do I mean by that? Well, so again, how many states are there? There is 4 states. In general, let's work this out. In general, for a given n, there is, for a given L, there is 2L plus 1 states. And for a given n, L can go from L equal to 0 to n minus 1. Okay. States with the same energy. I hope this addition is okay for you. Remember that if you forget this sum, the 2L plus 1 refers to the fact that there is 2L plus 1 states with different values of m for the same value of L. And now we have to count the number of L's. The number of L's can go from 0 to n minus 1. So what is this sum? This sum is, you can trivially work out what this sum is, because you know that the sum of n is just n times n minus 1 over 2, and this would be equal to n squared. So for a given value of n, there are n square states that have the exact same value of energy. Now, this is the connection between symmetry and degeneracy. There is a lot of degeneracy in the problem. So you can also work this out backwards. So suppose if you have a problem in which there is a lot of degeneracy, you can actually guess that there must be some symmetry. So for a given L, there is 2L plus 1 states that have the exact same energy, and this is due to the rotational invariance in the problem. Okay, what does it mean? This means that if you apply the rotation operator, you can rotate from the state L equal to 1, M equal to 0 to L equal to 1, M equal to minus 1. Okay, and you can rotate from the state L equal to 1, M equal to 0 to L equal to 1, M equals minus 1. So rotation operator mixes states with different values of M. Okay, and then we will talk about what a finite rotation operator is in the next semester. In general, that is a rather difficult problem, but for very low values of L, we can work this out. And the degeneracy of energy of the states with different values of M is because of this rotational invariance. There is a symmetry. But there is also another degeneracy in the problem. This has to do with the degeneracy in L. Okay, remember that L equal to 0 and L equal to 1 also have the same energy. Okay, this degeneracy is actually not due to rotational invariance. It is actually due to what is called the quantum mechanical equivalent of the Laplace-Runge-Lenz vector. So symmetries in the problem are rotation and there is another conserved quantity called the Laplace-Lenz vector. Okay, we will not talk a lot about this, but I will actually point out some literature to you. There is actually a very, very beautiful derivation of the hydrogen spectrum by simply appealing to the symmetries of the hydrogen atom. And this is due to Wolfgang Pauli. And Pauli simply used what is called the dynamical symmetry of the hydrogen atom to derive the energy values. If I can find a good paper, I'll point this out to you. It's actually a very beautiful derivation. Anyway, so what have we learned thus far? We have learned that if you simply blindly solve for the bound state energies of the hydrogen atom by solving the differential equation, you get stuck because your solutions keep blowing up. So you make a physical assumption that you want bound state energies you want bound state solutions that die down with distance, and you keep looking for solutions that have this property, which necessarily means that you terminate the series. And the termination of the series necessarily fixes some function of energy to be an integer, which you can then turn around and derive a value of the bound state energies. And you find that in this particular problem, the bound state energies goes like 1 over n squared. Hydrogen atom at a value is Z equal to 1. Okay, so there is a fundamental unit of energy also in this problem. And if you work this out, En would be equal to, this is actually quite famous, minus 13.6 Z square divided by n square electron volts. Okay, I'm sure you have seen this. And on all this, I'm actually assuming that mu is the electron mass. Okay, so I used the value mu instead of worrying about whether it is electron or nucleus, but it is actually the electron mass that is important in this problem. And tomorrow, when I begin the lecture, I'll spend about 15 minutes to talk about two-body problem in quantum mechanics because I didn't have time today. And I'll justify why it is okay to take mu to be the electron mass. Remember that if I'm looking at the hydrogen atom, there is two layers, right? The electron and the nucleus, the proton. So which mass should I take and what it is that determines the dynamics in this problem? It turns out that the object of primary importance that deals with the dynamics of the problem is actually the electron and not the proton. This is something that is also known in classical mechanics, but we will show this in quantum mechanics. Okay, and after showing this particular aspect, we will move on to the standard time independent perturbation theory starting tomorrow.